what I'm going to do now is basically, for the first half of this lecture, to just kind of draw up the pipeline little by little and go through all the stuff that we've learned about what happens in the pipeline, how we use it, what its effects are. Basically a recap of the entire pipeline that we've been doing or learning about for the entire course. After we've kind of done that, and probably spent quite some time on that, I want to look at kind of some of the kind of text questions we could imagine could pop up on an exam, like explain blending or what happens when depth testing is enabled or something like that, and kind of just put up examples of how detailed and what kind of answers I'd like for questions like that. Otherwise, I just kind of want to go through the entire material and kind of, through the course of today's lecture, just see the entire course in kind of one big image and what we've learned. Hopefully, for us all to see that it's kind of contained and not maybe as much as we feel that it is, or possibly for some to see the entire pipeline here and all the different algorithms and methods and calculations that we've learned, and make sure that it's at least kind of contained in this image. So I'm wondering if we can do this together, if we can go through the pipeline without me saying everything that's up here. Like, let's at least start rolling it that way. So if we just imagine that we've set up an OpenGL program, we've set up an OpenGL canvas, so to speak, and we're sending things through the pipeline. What's the first part of the pipeline that or basically let's start at the very beginning. What primitives are they that we send through the pipeline? What are we sending into the pipeline? If we just say our OpenGL pipeline starts here, OpenGL pipeline, what are we basically sending into it, or what are we connecting to it in order for it to start running? We want to now run the pipeline. What things do we need? What data do we need? Vertices, okay. So let's start there. We have vertex lists, as we've learned. Vertices. These can either be arrays in our own program code that we then link to OpenGL, or these can be buffers of vertices that we send down into the graphics hardware memory and then just send an ID to our vertices. Either way, we've set up a vertex list somewhere. We've told OpenGL what vertex list we wanted to read from. So vertices are being sent into OpenGL. So the first place where these vertices are used,
at the T.
Vertices, thank you. Vertices. So the first part of the OpenGL pipeline here.
Vertex shader.
Vertex shader, thank you. Now you two have answered questions. Now I'm going to force you to not answer them next until everyone has answered something. That means if someone wants an easy one, they're going to have to grab it before they end up being the last person here having to answer something later on. So vertex shader. Fair enough, that's the first thing we send in here. And in our vertex shader, we have attribute variables, attribute vec for something or the other, position, normal, UV. And these attribute variables in general are filled by values from these vertex lists, right? So vertex lists put into attribute variables. We can set an attribute variable to not be read from the list and instead set a specific value to it. Some students have used this simply to kind of decouple the UV attribute from the vertex list so that they sometimes have the UV attribute here as well, and that goes in there. Sometimes they just switch it off and say UV is not read from a list. But then usually it's just because they're not using it. In some cases, we might actually kind of decouple the normal from the vertex list and just set a single value if we have kind of a big, a lot of polygons that are in the same plane, something like that. Either way, in general, the way we've been using it is we have attribute variables that are read from these vertices. What other types of variables do we have in the Vertex Shader? Okay, uniform, let's start with that. How do we use those? Something like uniform matrix 4x4 here. We have the model matrix, we have the view matrix, we have a projection matrix. So our uniform variables are basically variables that we just set whenever we want. So attribute variables read from list, uniform variables that we set. Someone said varying variables. In the first case, or in our simplest shader, we just said, okay, we have varying vec4 color, but we can have all kinds of other things here. Varying variables are variables that we set in the Vertex Shader, but then use later in the Fragment Shader. Okay, so these are types of variables. We have the main function, but apart from kind of the way the code works, I'd like to maybe write up what happens. So, what happens in the Vertex Shader? If we kind of leave some space for that here, to just draw it kind of as an image rather than anything else. So if we just look away from the code and imagine what is it that happens to the vertices in the Vertex Shader. Now you have to answer this question, either one of you. Vertices sent into the Vertex Shader. Let's stop writing code and just say what happens to them, like what geometrical things happen to the vertices once we're in the pipeline. Or the position, let's say. I'm looking at the position now. The position is kind of the geometrical location of our vertices. Let's worry about the normal later, because that's mainly for lighting calculations. So what happens to the position?
Get set to a position, then we use it to find what? We use it to find the view matrix and.
Not quite defined. We have the model matrix and the view matrix.
We use the view matrix and model matrix and projection matrix to change the way we see the position in our world.
Exactly.
From the global coordinates to the local.
Yes. So we have what we call local coordinates that are sent in here, the original coordinates that we get in here, local, and we multiply them through the model matrix, which is one of our variables. So model matrix giving us the global coordinates, basically same point, except it's expressed as if it's in our kind of global coordinate system, whereas we have this point here when we send it in as if it's expressed in its own local coordinate frame. And that local coordinate frame is then represented in the model matrix. Take it from local to global. And as you said, we have the view matrix, taking it to what's called I coordinates. We have the projection matrix, sends it into what's called clip coordinates. And clip coordinates are what OpenGL understands, so we can send it out of our Vertex Shader where we can program whatever we want, and into the OpenGL pipeline again, kind of the base OpenGL pipeline. But then we have to make sure they're formatted in a way that OpenGL understands. And the main thing here in clip coordinates is that anything that we want to be seen and not clipped away should have values on x, y, and z between -1 and 1, -1 and 1, and also kind of in the z dimension here. Trying to get this. So, okay, from -1 to 1, this dimension as well. So everything that's within this box will in the end be rendered to our screen, as long as it's not behind something or some other tests fail. In general, everything that's outside this box will be clipped away. Things that are kind of partially within this box, polygon that looks something like this. In the end, it'll be clipped here, and so this part of it will be clipped away. And we only have the part of the triangle that's inside this box. So that's the idea of clip coordinates, and OpenGL understands them that way. We can also say, since clip coordinates are homogeneous coordinates, where we have x, y, z, and w here, because this is not necessarily 1. This holds true if this is 1. If we take all of them and divide them by w, we want them all to be between -1 and 1 in all dimensions. I could also say I want the homogeneous coordinates to be like this, and I want them to be in the range, like x, y, and z should be in the range ranging from -w to w, from -w to w. It's just two ways of saying the exact same thing. So if I take the homogeneous coordinates and shorten them by w, so I get a 1 here, then I want the output here to be between -1 and 1. I can also say that's the same thing as saying I just want this unchanged point here to have values of x, y, z that are between -w and w. So these are the clip coordinates that we send out of the position. So the geometrical transformations that happen in the vertex shader, we have variables for the model matrix, variables for the view matrix, variable for the projection matrix, and these are simple matrix multiplications. So global coordinates equal the model matrix times local coordinates. I coordinates equal the view matrix times global coordinates. Clip coordinates equal the projection matrix times I coordinates. And we can, combine some of these and do it in one calculation or whatever fits our shader. But what else do we have to do in the vertex shader? Or if you were drawing this up, would you now continue with the geometrical transformations all the way and then kind of do another pass to look at what other things we need to do in the shaders? Or would you rather kind of do it from right to left? Or to phrase it differently, what's next? What should I draw next here? I'm again going to force this from someone who hasn't already answered.
So I'm free from answering.
So you're free from answering. Unless you have the answer and want to, you can raise your hand, and if I have to wait too long, I might call on someone who has already answered.
Do you want to do the fragment shader next?
So I could do the fragment shader next, but the fragment shader is kind of somewhere way over here. So I kind of like to get a connection to the fragment shader first. We can actually do the stuff that has to do with the fragment shader and lighting and things like that. We can just do it in a second pass. So if you just do the geometrical transformations, what would happen next here to our clip coordinates? Sure.
We actually clip them. So OpenGL actually.
Okay, so OpenGL clips them. So I'm going to add, the colors are getting mixed up here, so I'm going to add just clipping. So we have a clipping algorithm here. This is implemented in OpenGL. So while the main function of the vertex shader is something that we need to implement, the clipping algorithm is just implemented by OpenGL. It just happens in hardware. The only thing we need to make sure is that the clip coordinates make sense. Again, not all of these have to be, x, y, z have to be within the range from -w to w. Just if they're not inside that range, they will be clipped away in some way and if all the vertices of a polygon are outside that range, it'll just be thrown away entirely and we don't have to continue. So clipping takes care of that, takes care of actually clipping things away. So if we're looking at this in terms of an exam, like we like to know the Cohen-Sutherland clipping algorithm. So we're going to know and understand that clipping algorithm and be able to kind of implement it by hand for some simple setup of a window and coordinates. However, the Cohen-Sutherland clipping algorithm is a fairly simple two-dimensional clipping algorithm. So it's not entirely what happens in the actual OpenGL clipping, but it's close enough for us to have a handle on what happens here. So on an exam, we might actually have to implement that, or not implemented, but, well, possibly implemented, possibly explain its implementation, or possibly just take a few particular values and send it through the Cohen-Sutherland clipping algorithm. So what's next? The things that we've looked at. Someone who hasn't already answered. What's the next box? We still have clip coordinates here, they're just clipped now. Otherwise, they're the same coordinates.
We need to get into window coordinates.
Yeah, well, they're in the window here, yeah, but we need to get into kind of viewport.
Viewport to window.
Yeah, window to viewport mapping.
Window.
So window to viewport mapping. So we need to understand that as well. There's a window to viewport mapping to viewport mapping method that we need to understand how it works. If we have a given window and a given viewport and some points, we need to be able to say what will the coordinates of a certain point within this window be on the viewport, like in which pixel will this end in the end. So we're going to know how to kind of implement that or go through that by hand. So let's do, before we go into the last part, let's look a little bit at each of these coordinates. So local coordinates, they are 3D continuous coordinates. Global coordinates, they are different coordinates for the same points, but still three-dimensional continuous coordinates. I coordinates, again, we're just taking these three-dimensional coordinates and we're twisting them around in a three-dimensional space. Still three-dimensional continuous coordinates. What about clip coordinates? Like, what are they? We've kind of taken this three-dimensional image and through the projection we've projected it onto a two-dimensional window, right? But we've made some kind of pseudo depth that goes along with it that also fits this bill of kind of is the z-value here. So I like to view it as two-dimensional continuous coordinates. So we're not into discrete space yet. We're not looking at just particular pixels. But we have kind of linked to it at this point pseudo depth, which we can use for the depth test. In this particular case, we have the varying variable color here. You can say, so we have the color, or more specifically, we have just all the varying, we have values for all the varying variables. So at this point, we have two-dimensional continuous coordinates. Those are the clip coordinates. We still have those here. So basically, same thing here, except we've clipped some of them away. Now the question is, at this point, what kind of coordinates do we have? Yeah, so I'd call these, I'm going to allow myself to call these two-dimensional discrete coordinates. And say this is basically, these are coordinates that actually correspond to particular pixels on the screen. Depending on implementations, these might still have fractions. We use those fractions to kind of decide on things like anti-aliasing, like is it exactly this pixel or is it between pixels? But for our purposes, I'm going to allow myself to say we're now in pixel space. We're just working with particular fragments here. So, what's our next part here then? Somebody who hasn't yet answered.
Rasterization.
Rasterization. What does rasterization do? Like, not on the algorithmic level, but what's its purpose? I'm going to wait a moment before I call on you. Anyone else? You answered rasterization. Do you have the explanation as well? Cool. Oh, sorry. Somebody? You go then. Sorry?
Per pixel calculation?
Yeah, we're going to per pixel calculations, but we're basically taking, to do my explanation of this, would be at this point, kind of have just the corners, just the vertices of our polygon. But what rasterization does is it basically fills these in. So it fills in all the pixels, and it needs some way to calculate a value to put in each of these pixels. So originally we just had the corners. Rasterization fills the entire thing in. So the algorithm, what it does is it kind of starts at the bottom, goes to the top, and takes scan lines that cover the part of this polygon that is supposed to be filled in. But for every single pixel that is covered, it finds a value to be put into our frame buffer. The way that value is calculated depends on how our pipeline is set up. In the static pipeline, it's simply linearly interpolate this color that we have here and set that value here. But what we have instead is we have the fragment shader. I'm going to give that a little bit more room here. So the fragment shader also has uniform variables, basically variables that we can set. For instance, you say it has a variable vec for something like material diffuse, uniform vec for light specular, things like that. Light position, or possibly the light position would be in the vertex shader. So we have these uniform variables that we just set values for, so that these will be the values that our shader program uses when we draw the next object. But it also has varying variables, and those varying variables, like varying vec for color, have to be exactly the same varying variables as in the vertex shader, because, and this is an important thing because this might be a question on an exam, the connection between the vertex shader and the fragment shader is through these varying variables. So every varying variable that we define in the vertex shader has to have the same corresponding varying variable in the fragment shader. Any value that we set in the vertex shader will, during rasterization, be linearly interpolated for each pixel. And for each pixel, those linearly interpolated values will be set to that same varying variable in the fragment shader. And then we use that for our calculations. In the end, our fragment shader gives a single value that it calculated from the values that we had. And that is put in the frame buffer. But if the question was, what is the connection between the two? This would be the answer. For every varying variable in the vertex shader, a value that we set to it in the vertex shader is linearly interpolated for each pixel during rasterization, and those weighted averages of the values are set to the variables in the fragment shader, which uses them to calculate a color per pixel. There was a question? Okay. So that's kind of our connection, vertex shader to fragment shader. And this is something that I'd like everybody to kind of understand and be able to explain, even just in short text like that, just to be able to kind of put your finger on how these things link up and what connects them. So rasterization, basically for y from y bottom to y top. Inside that we find some values for left and right. Then we go for x from x left to x right. So we're doing linear interpolations here. So from the bottom to the top, we're doing linear interpolations of values to find the left value and the right value in a scan line. Then for every x, we find values by linearly interpolating between the left value and the right value, and then we go one pixel here, one pixel here, one pixel here. So we're filling in the pixels between them. For every single pixel, we find these values. Then we run fragment shader, which is basically our fragment shader here, meaning that we found values for the varying variables set them to the varying variables in the fragment shader. Then we run the fragment shader's main function, where we calculate whatever we want. And in the end here we say GL frag color equals something, and we can calculate that in any way we like. There are particular light calculations that make sense and give us a kind of expected output here, but we can in effect do whatever we want here. So we set something to GL frag color. In the same way as we can go ahead here and say the clip coordinates, go down here and say in the end of our vertex shader, we need to make sure we have a line that says GL position equals something, but that something is actually going to be the clip coordinates. So we set GL position here, which is kind of the main function of the vertex shader, to get a position. The secondary function of it is to set values to varying variables. We go into the fragment shader. The main function of the fragment shader is to end up with some GL frag color for this particular pixel. Obviously, it uses the values from the varying variables to do that. But in the end, we could skip all the varying variables and just set black to this. And just have a basically black and white image, not grayscale, something like that. And we still have the whole functionality. But of course, we're more interested in actually having some values here that are basically gradient interpolated over the polygons themselves. All right, so I think more or less we're now at the point where we can say we're sending in vertices. They go through the vertex shader. At this point, we kind of wait until we have the correct number of vertices. If we're doing triangles, we send one through, we wait, we send another through, we store that here, we send the third. Once we have three together, then we send them together through clipping, through into the viewport, and through rasterization, because they're a set, they're a triangle. If we're doing lines, we take 2 and 2. So at this point we can say, if we take 3 and 3, we can do the clipping, we can do this, we can fill in the color, we can at least fill in what pixels should be filled. So we have the correct geometrical positions of everything now. So what's missing of the stuff that we've done this semester into this to do something more interesting than just saying, I know which pixels will be affected? I want to say kind of, I also know how each of these pixels will be affected. So what do I need to add in kind of into this entire picture? Not a particular box, but just a particular set of calculations that I've kind of skipped over, so to speak. Because I've only been looking at the position until now. Yes, you can answer.
Lighting or mapping?
Okay, let's start with lighting. So inside here, I kind of didn't leave enough space here, so I'm gonna take this 3D continuous here. Just say all of these are 3-dimensional continuous. Better space for this. So these are my clip coordinates that I put into GL position. So I'm going to leave a little bit of space here for lighting calculations. So now I'm putting lighting calculations into the vertex shader. Is that the correct place for them? And where would we put them? I can answer this. The static pipeline would have done them here in I coordinates, lighting calculations. We, in general, find it simpler to think of them in global coordinates, because then we can just set up the light positions and the camera positions in global coordinates, send our local coordinates into global, and it's a nice place to do them. So we're going to be imagining that we're doing our lighting calculations. I need a different color. Our lighting calculations in global coordinates in the vertex shader. The lighting calculations will give us a value for this varying variable color, and that color will be linearly interpolated onto all of these, so we get a different color for each. If we have, basically we can say GL frag color. Now I'm worried that this won't be on the video, but either way, GL frag color just equals V underscore color. Let's call it that, V underscore color. V underscore color. So we have this varying variable color. We calculate the value for it here. OpenGL will calculate the linearly interpolated values for it here, so we can just set that value to frag color, and we have a gradient. We've done lighting calculations per vertex, and then we do a gradient between those, weighted averages between those, so we get a smooth shade over the polygon. So that's per vertex lighting. What do I need to change to make that become per pixel lighting or per fragment lighting? Okay, so I have to set something else into the varying variables. So instead of just doing the lighting calculations here and having this varying variable, instead I'm going to set up different varying variables here. Say, which ones would I set up as varying variables now? Someone new? What would I like to linearly interpolate instead of the final color? Okay, somebody who has answered.
We set in variables to calculate the rough S.
Okay, so yeah, so S, which is a So basically, we have three variables that are, rather than them being a color, they're geometrical objects, they're vectors. So one of these would be the normal itself. I'd say I have a normal to each vertex, but I'd like to have a normal to each pixel instead. What else? I'd like to linearly interpolate the normal, S, as you said. But what vector is that? It's a vector from the vertex to the light, okay? So let's say V underscore S here, this is a vector to the light, and either V underscore V, which is the normal to the camera, or the halfway vector, doesn't matter, this depends on our lighting calculation. So we're taking normals, we're taking kind of geometrical directions, and we're setting those for each vertex and allowing OpenGL to linearly interpolate those. So instead of a color, we now have these vectors, normal, V underscore S, V underscore V. So instead of calculating the color here for the vertex and then linearly interpolating the color, it's going to be a little bit more expensive because we're going to calculate fewer things. We're not going to actually do the lighting here. Instead, we're going to prepare lighting calculations in the vertex shader by calculating the correct normals for each vertex. We're going to allow OpenGL, the rasterization, to linearly interpolate not the color, but these normals. So we get different sets of normals for each pixel. And so we have different intensities of values like Lambert and Phong, which are based on the connection or calculations from those normals. Make sense? So now we're doing this. In that case, we don't just do GL frag color equals V color. Instead, we do lighting calculations here. And say GL frag color equals something that we get out of the lighting calculations. So again, here's a question that we could imagine answering. Like, what is the difference between per vertex lighting and per fragment lighting? A very short answer here is simply, in per vertex lighting, we finish the lighting calculation for each vertex using these geometrical data that we have in the vertex shader until we calculate a single color in the vertex shader. We set that to a varying variable and allow the rasterization to linearly interpolate the color over all the pixels, giving us a gradient, but not giving us kind of different lighting effects on a single polygon. Instead, the lighting effect just affects the vertices, and then we get a gradient over the entire thing. Changing that to per fragment lighting means we need to take some of that geometrical data, and instead of finishing the lighting calculations here, we just prepare them by setting variables with normals. Those normals are linearly interpolated, so we get weighted averages not of the color, but of the normals into these variables. Then we use those values to do the lighting calculation for each fragment, for each pixel in the fragment shader. But the lighting calculations are the same, and they're using the same data. We're just doing them more often, and this data here is averaged over all the pixels. In the end, we do the lighting calculations in the fragment shader, using values from normals that we linearly interpolated from values that were set in the vertex shader, calculate a color here, and that is the final fragment color, rather than the final fragment color just being a linear interpolation of the colors for each vertex. All right, so what do we got? These are things that we've learned about. We know how they work. We know how we send vertices into OpenGL. We know how we multiply them with a model matrix. Another thing with a model matrix, we understand how we do transformations. Transformations like scaling, rotating, translating. We can add those together into combined transformations in a model matrix, send those values for the model matrix into the shader, and all of those will affect the local variables when we send them into global variables. So we know how to set up a model matrix, and we also understand how they work in the shader. View matrix, again, we know how to set up a camera or eye. We know how to make sure that that eye is positioned in a specific place, it's oriented in a specific way. We know how to take those values, its point and 3 vectors, set them up in the view matrix, so the view matrix will actually go from global to eye coordinates, which are basically the camera's local coordinates. Projection matrix, we know how to do a perspective projection. We know how to set that up. We know how to take a specific angle for the camera, a specific ratio of our screen, near plane and far plane, use those values to set up near, far, right, left, bottom, top, and set up the correct projection matrix using those. So we can do all of these. We can solve a problem that basically says, I want a model matrix where it has been, the coordinate frame has been scaled like this and translated like this and rotated like this. I want a view matrix where the camera is positioned here and looking at this, and this is the up vector. I want a projection matrix where this is the angle of the camera, and so on and so forth. This is the near plane and far plane. I want to see the corresponding matrices that we get for each of these. And if I were to send in a vertex with these coordinates, I want to be able to calculate it throughout and say what will be the clip coordinates for that particular vertex. Yes?
I'll test if you ever make us do a model matrix.
A model matrix?
To make a model matrix out of like rotation and scaling.
Sure, yeah. Probably not very complex combinations, but if you look at the exams that I've already put online, like that we did the hand-ins out of, you can see more or less probably in every single one of them, there's some version of that. Like, what will be the matrix if I do this rotation? What will be the matrix if I do this transformation, or translation? And if I do this one first and this one next, what will be the combined matrix that does both of those for me? Yeah, definitely. You can get that. You can get set up a certain view matrix, set up a certain projection matrix. I know on a test, if we do all of those 3, the odds of somewhere being a little error that you made are huge. So if I then give you a vertex and say what will be its clip coordinates, a lot of the time, even though you did everything pretty much correctly, some minus you forgot, something like that, will mean that there will be a lot of versions of this. I'm fairly lenient on that. I'm just looking that you did the correct calculations at the right places. So often it's not great on an exam to have these kind of combined problems where the last part hinges on you having done all the other parts correctly. So I tried to make sure that if one of these isn't correct, you can still finish the last. But you can get these, make all these matrices, and send a vertex through the vertex shader and tell me what will be the value of GL underscore position with this setup if these are the coordinates that I send in as local coordinates for this vertex position. So all of this could be something also. Instead, I might say, okay, I'm not going to have you do that by hand. Instead, I'm going to say, how would you set up a small function that would make this translation or transformation and put it to a matrix? Or instead, I have a vertex shader fill in what's needed so that it uses the model matrix correctly and uses the view matrix correctly. Fill in the variables that are missing and the code that's missing to the main function so that this works correctly. Any of these could work. Or I have a vertex shader that has all the geometrical parts correct, and I just say, go ahead and fill in lighting calculations so they work correctly, depending on these and these factors, or these and these variables. And either make them be per vertex lighting calculations or make them be per fragment calculations. Any of these could be potential exam questions. All right. So all of these, know how to make these matrices, know how to use these matrices, know how vertices go into the pipeline. Understand the base lighting calculations. If you have this normal and you have this position and this light position and this camera position, you can calculate Lambert, you can calculate Phong, you can calculate the intensity based on these. Going onwards, we've looked at how the Cohen-Sutherland clipping algorithm works, so that's something you need to be able to work with and understand. We know how window to viewport mapping works. We'd like to be able to calculate that. Rasterization, would even like to do something like, you have these 3 points, P1, P2, and P3, and they all have these particular pixels, and they have this particular color or this particular value for a varying variable, and then simply say for the pixel, something xy here, what will be the value of that varying variable? What will be the color for this pixel if we have positions for P1, P2, and P3, and colors for P1, P2, and P3? What will be the color of pixel x, y? So then you don't have to actually go through these entire for loops, but you have to say, well, if I'm inside this for loop here, going from y bottom to y top, and I can see my y value will be whatever value was set here, I can find the values for that particular iteration through the loop. That means I have left and right values for this particular scan line. Then I can imagine that I'm doing that scan line, and right now I'm at the x, which equals this x. I can find those values using linear interpolations. That means I can find what value will be put into the varying variable here. So calculate yourselves through a single step of the rasterization. Understand where you are in the rasterization. It's something we'd like to be able to do. So at this point, are there questions to begin with? And maybe, does this feel like a lot? Or does drawing it up on a single whiteboard feel like, okay, we did a lot this semester, but at least we can contain it in a single whiteboard here? It's not so much. It's a few algorithms, a few calculations, and we're good. Nobody have a handle on that? When did we start? I think it's time for a short break. If there are no other questions regarding this, let's take a short break. You can look at this image or take a picture of it or just look at the video later. And after the break, I'm going to go through a few kind of imagined text questions that could be on exam and kind of explore how we would answer those. All right.
Ja, daar weet ik nog wat dat dat wordt irriteren.
Jag tror bara det var något.
Ja. Nej, dat was dat wel eens weer of zo. Dat is natuurlijk wel wissels.
Lägger.
Ja,
Så det är som en journalkontroll, ungefär makar och lägger långt ifrån.
Okay, so I'm going to leave rasterization up here for a while because there are kind of things that might fit in there. We didn't completely finish, for instance, depth testing and blending there. But I'm going to set those up kind of as kind of imagined text questions. So if you're in an exam and you get the question, explain, let's say depth testing. Depth testing and its associated or its calculations. Oh, I'll skip that. Let's try to keep it short here. So explain depth testing, for instance, where its calculations happen, what calculations those are, what's its effect. That's something that's important not to forget. If you're asked to explain depth testing, it's nice to start with what's the effect that I want out of it. Let's start with kind of not from the point of view of someone who's implementing it, just start at the top and say someone who's using OpenGL, what does he expect to happen if he enables depth testing? So what's the effect of depth testing? What are we looking for here? Sure, yes?
Things that are closer are drawn on top of things that are further away.
Okay, so things, or closer, things, obscure, further away, or things further away. Okay, so closer things, obscure things further away. I'd add here regardless of drawing order. So regardless of in which order I send them into the pipeline, I still want the one that is perceived to be closer to be drawn on top of the one that is perceived to be further away. So either I draw the closer one first, and when I draw the further away one, parts of it are skipped so that it's behind, or if I draw the one that's further away first, the closer one will obscure it or will overwrite it. Okay, so that's the effect. Then something like where in the OpenGL pipeline do its calculations happen? So where do calculations for depth testing happen? Or where does the depth test itself happen? Let's start with that. Okay, so when we're creating the clip coordinates, that's where we calculate pseudo depth. So yes, let's start with that. So pseudo depth values calculated, we can just say during projection, that's okay, I'll understand that. So basically when we're taking our I coordinates and multiplying them with the projection matrix, we get X and Y clip coordinates, which were our two-dimensional coordinates, but we also get the Z coordinate, which is our pseudo depth. So okay, that's where this value is calculated, but where does the test happen? Like the test doesn't happen for each vertex because we need the test to be more detailed than that. So where does the test happen?
Rasterization.
Okay, so the test happens, so let's say here the test itself happens in rasterization. If I wanted you to be a bit more specific, like after what, before what, where would you say the depth test happens?
In the algorithm over there, and it would discard it before running the fragment shader.
Okay, yes. So before we run the fragment shader, we want to be able to discard based on depth. So I'd say it's enough to just test itself happens in rasterization before running fragment shader. All right. So now, but what happens in between? The test itself happens before we run the fragment shader for this fragment. Is there a little bit of extra information that we can put in there to make sure that we're 100%? We calculate it per vertex during projection. You can say that per vertex. The test happens per fragment, but kind of how do we get from per vertex to per fragment? Nothing detailed, we don't have to go into the scan lines and stuff. But what I'd like to add here is just during rasterization, we either find weighted averages for each pixel based on those values, or we linearly interpolate the vertex values for each pixels. So during rasterization, linearly interpolate vertex values to find, so that's just generally what happens in rasterization for any value, but just to specifically say this also happens to a pseudodepth. To find fragment value, or fragment Z or something like that, just find the pseudodepth for the fragment. Then we say the test itself happens before running the fragment shader. All right, so we have these places. We calculate this. The only thing I'd like here is a little bit of a how. Can we just in a short sentence say, what is this test? How would that sentence look? Somebody? Anybody? Whether you answered before or not, it's okay. So we have a value for this fragment, pseudodepth value for this fragment. Yes?
If the value for this pseudodepth is less than the value stored in the Z buffer.
Yes, okay. So that's kind of what I'm looking for, is there's a buffer there that holds those values for us for each pixel. So we look into that buffer, which is our Z buffer, and say if this fragment pseudodepth, and this doesn't have to be exactly phrased like this, but if this fragment pseudodepth is less than, we can say then what is currently in the Z buffer at this location, or we can just say then Z buffer number xy for this fragment. Then we do what? Then so we got the if sentence, if it's less than the Z buffer. Do you want to finish? Like, what do we do then?
If it's less than the Z buffer, then something has been drawn which is closer to us, so we skip it.
I usually view it the other way around, that a lower value is closer.
Okay. So then you override it.
Yeah. But if you mix those things up, it doesn't matter. Okay.
Yeah.
So then, if it's further away, then I'd say we run the fragment shader, continue with this fragment, then overwrite value in frame buffer. So we overwrite frame buffer number xy with this fragment value, and we also override the depth buffer in this pixel with this pseudodepth. So and Z buffer number xy. You can phrase this in some way that it makes sense. Z buffer xy equals this pseudodepth. So our pseudodepth for this value goes into the Z buffer. Let's just take this here over here, because if it's closer, then we override both, right? Then we override the frame buffer and we override the depth buffer. If the new value is higher than the value that's already there, if it's further away, do we do anything at this point? No, then we don't override the z buffer with a new value because we already have one that's closer. We also don't override the frame buffer, so we simply stop. So else, you can say else do neither, or we can say otherwise. We basically jump out of this iteration of the fragment shader or iteration of the rasterization star and just go into the next pixel. So we discard this fragment. Do neither, or we can say discard the fragment. So however you phrase this, what I'm kind of looking for is it's calculated during projection. The test itself happens in rasterization before we run the fragment shader, and the values are linearly interpolated from the pseudo depth that we calculate to the pseudo depth that we use per fragment. So that's one thing. And then if this fragment is smaller, we override both the frame buffer with this value, or we run the fragment shader, we override the frame buffer, and we override the depth buffer. So I'd like to see all those things. Otherwise, we don't run the fragment shader and we don't override the frame buffer. Otherwise, just do nothing. But to make sure that run fragment shader, override frame buffer, and override z buffer or depth buffer, all of these happen in order for this test to work. We have to update all the values or just stop and do neither of them. Continue to the next pixel. Questions regarding this? So this is an example of some kind of question. Explain depth testing. It can be phrased in different ways, but this is kind of the general idea. So we've kind of said we find the values. We can say we have a depth test here as well. Depth test. Or GL depth test if we want. This is happening here before we run the fragment shader.
Here we are doing opacity checks.
Yes?
How would that affect? Do you just not use the C buffer, or do you?
If we're also doing blending at the same time, or checking for opacity, I'd say in some cases you like to use both. Some things are semi-transparent, but they can also end up behind or in front of things.
Would you be updating the frame buffer and z buffer and just update the value that's in the frame buffer with opacity, and just the value has changed with something and with some color and some opacity color on top of it?
Like
the
blending.
Fragment shader is run.
So if the depth test fails, we don't continue. If, however, you're doing something like sometimes like an explosion particle effect or something like that, there's just particles all over the place, you might want to just turn off depth testing when you draw that to make sure that all those particles overlap. Or you might want to order them from furthest away to closest in order for them to kind of mix up and blend. But if we have depth testing turned on, depth testing will come in first, and then blending, which will in some cases mean that things won't blend that you expected to blend. Then either you have to turn off depth testing and make very sure that you're drawing things in the correct order so you don't end up with a fire that's behind a wall being seen through it. So if you turn off depth testing, you have to make sure you're drawing things in a good order. Or instead of turning off depth testing, you can also have it turned on, but just make sure that then you draw transparent objects after you draw all the non-transparent objects. And if you have multiple transparent objects that might blend to each other, you have to make sure you draw those in an order from furthest away to closest to make sure that they get written on top. Because if you draw something that's closer first, even though it's transparent, then draw something that's further away, depth testing will clip it and blending will never happen. So that's the way it works. But if you want something that's further away to also blend, you just have to either turn off depth testing or make sure that the order is correct. Does that answer the question? Or so let's look at blending next since we're talking about that. So let's again have this a very general question here. Explain blending. So based on the previous answer, kind of what first important part would I like to explain?
The effect of it.
Okay, so just what am I looking for? Regardless of calculations and the pipeline, just what do I want? If I, as a programmer, turn on blending, what do I want to see?
Opacity.
I want to see opacity. I want to have objects be transparent or somehow mix with one another rather than override or be obscured by one another. Okay, so the effect is, we can just say, I want things to be transparent. Transparency, I want to be able to control opacity. I want to be able to set a particular value, like the alpha value, and control something's opacity. Color values, color is mixed rather than obscured. So instead of overriding things, I want to mix with them. That's the effect I'm looking for. I want to be able to draw things and have them mix with whatever's in the background. Just do the same thing here. Where in the pipeline does this happen? So where does blending happen? Fragment shader. Does it happen in the fragment shader?
The rasterization.
Well, within the rasterization, yes, okay. The fragment shader is here. We can affect blending with values that we can calculate in the fragment shader. OpenGL can do blending for us. We don't need to actually do the blending ourselves within our main function of the fragment shader. So instead we can say we have blending, or GL blend, if we want. So if we enable GL blend, we're affecting something that's going to happen within rasterization for every single pixel. So it's happening per fragment in the rasterization, but it's happening after we run the fragment shader. So it happens per fragment.
Does it happen per pixel?
Yes.
Does it have to know then what pixels surround it for the blending to work?
You're not blending, like if you have 9 pixels here, you're not blending this pixel with the pixels around it, like a blur effect or a focus effect or something like that. That's more complex to do, and I haven't really covered that kind of thing. You're blending basically whatever color we calculated here and we're about to put into this same pixel, we're mixing that color with the color that's already in that same pixel. So instead of blending kind of things that are around each other, we're blending things that I see in the exact same place. So I'm blending kind of distance blending. So I'm blending something with what's behind it. I'm not blending it with what's around it. That's a different kind of thing that we could do in the fragment shader, but I haven't really covered specifically. So blending is basically taking what's in the same pixel that I'm going to put down now. So I'm doing it per fragment in the fragment shader, and I'm mixing the fragment that I'm getting out of the fragment shader, the frag color that I got out of the fragment shader, I'm mixing that with whatever's already in the frame buffer. So instead of just putting it into the frame buffer and obscuring it, or throwing it away if it's behind, I'm taking the two colors, I'm mixing them together and then putting them back in. So I'm mixing something with what's behind. So it happens per fragment. During rasterization, after running the fragment shader. So during rasterization, after fragment shader, is where blending happens. So we have our fragment color. We've set our fragment color, and we've probably also set the fourth value of the fragment color, the alpha, and that's in most cases something we're going to be using in blending. We can also just blend things together. We can set the blend factors as GL1, GL1, and then we just take this color and add it to the other color, and we just have everything, light everything up. So this is where it's not as complex the where as in depth testing, where some calculations happen in one place, other calculations happen somewhere else. Blending just happens here. The how might be a little bit more complex. If this was just explain how we implement transparency, then we could just say, okay, I take the alpha value from the fragment and I multiply that alpha value with the fragment color that I'm sending in. I take 1 minus that alpha value, basically the rest, and multiply it with whatever's in the frame buffer. I add the two together and I put that into the frame buffer. But in blending in general, I kind of have to say, instead of overriding, let's say frame buffer number xy with GL frag color. So instead of overriding it with GL frag color, we do, then I can just say frame buffer, and it's okay in some cases just set up a small equation. Can explain a lot more than phrasing everything. I just say the frame buffer number xy equals some source factor times GL frag color plus some destination factor times what's already in the frame buffer number xy. Okay, so I take what's in the frame buffer, multiply it with some destination factor. I take the fragment that I've made now, GL frag color, which I just made in my fragment shader. I multiply that with some source factor. My current fragment is the source. What's in the frame buffer is the destination. Multiply each with a factor, add the colors up, and then I put that into the frame buffer. However, we need a little bit more of an explanation for what these source factors are. It doesn't have to be detailed, but just say the source factors, or the factors, source factor and destination factor, can be different values based on function GL blend func. Should be a song though, GL blend func. So we need to write that one. GL blend func here, we could say source factor, destination factor. So based on whatever we send in here, explain that somehow. Different values based on this. For example, GL source alpha is basically GL frag color dot A. It's basically the alpha value of the frag color. Or GL, do 1 minus source alpha. And maybe just put an example. Say if we use GL source alpha as the source factor, GL 1 minus source alpha as the destination factor, we just get regular transparency. Because we take the alpha value, which says how opaque is this, and we take the rest of it and do a weighted average with whatever's under. If we have an alpha value of 0.2, for instance, the new color will be 20%, the old color will be 80%. We mix those together for 100% value. Or you can take an example, if we do GL source alpha and GL1, it'll be multiplied with its alpha value, but then just always added, or something like an energy effect. Do you feel like there's something missing in this explanation? So, This kind of fills up what we've looked at in the rasterization. Yes, question?
Question about generally when blending happens. So if we have, say we have depth testing enabled and blending enabled.
Yes.
And we now have a fragment with which is far behind than what we already have in the buffer. Does this now get?
It just gets thrown away.
Gets thrown away.
Yes.
Even though we have blending enabled.
Even though you have blending enabled. So if you have both blending and depth testing, I can draw an image here. My camera is here. I'm looking here. Let's imagine I want, for instance, this to be transparent, and then there's a solid object behind it.
Mm-hmm.
Because it wouldn't really matter if I have a transparent object behind it. Well, for instance, this. If we drew this first, and then we draw this solid object, since we have depth testing turned on, will simply be thrown away. So this will never be seen and won't be seen through it. Because we can't really do blending backwards. Because, well, you could do it, no, then you'd have to turn off depth testing. As soon as you turn off depth testing, or another thing that you could do is you could clear the depth buffer. You could draw your transparent objects first, then clear the depth buffer, then put things in. But then you'd have to switch this. You couldn't use source alpha and 1 minus source alpha. You'd need to use 1 minus destination alpha and destination alpha. If you're blending when you already have a transparent object in, and you want to do the solid objects afterwards, kind of have to turn it backwards.
Yeah.
It's possible, it's a little bit more complex to think about it that way. But sometimes you want depth testing. For instance, if you have a solid object here that partially obscures this object, the best way to do transparency so that it works with depth testing is to take all objects that don't use blending or have a full alpha value and just draw them first, then draw your transparent objects. In that case, you draw this first, then this, and this would be the third thing you draw, which means that here, when you're drawing these pixels, the depth value will be higher, which means you pass the depth test, so you continue, you finish running the shader, then you blend this with what's behind. However, when you draw this pixel here, you'll already have drawn this, so this is closer, so this gets obscured. If you just turn off depth testing, then suddenly this object will also be viewable through this, and that doesn't make sense. So very often you'd want to have both blending and depth testing, and that's a good thing because you've drawn the solid objects first, then you draw the transparent objects. Depth testing means that your transparent object won't be seen through this, but the order in which you draw, that you drew the solid objects first, make sure that this object will be seen through the transparent object. But when you get into things like energy effects and stuff like that, if you have to have depth testing on to make sure that things don't get seen through the wrong things, then you're going to have to do things like actually order not only your objects from furthest away to closest, but sometimes you have to order the polygons within your objects from furthest away to closest to make sure that it works. And there are systems that do this. So, you know, that's not something that's ridiculously heavy or computationally complex to do. But, you know, if you can do something else, if you can just make sure that the order is correct, then that's cheaper than ordering all the polygons within. But sometimes you have to do that. In some cases, you know, this might be a sphere, for instance, and you want it to be transparent. You want to see kind of the back side of it through the front side of it, right? You also want that to be transparent onto itself. So that means maybe you can take this object, and you can find out kind of where it switches from being a front side to a back side. And instead of drawing all the polygons in an order from closest to furthest away, you can just draw first all the ones that are kind of more pointing away from you, then all the ones that are more pointing towards you. That's not too complex. You can just go through all of them and first discard all the ones that are pointing towards you, then just draw the whole object again, except then discarding the ones that are pointing away from you. Then just do these first, these second. It means 2 passes through the polygons, but it doesn't mean an extra pass through the entire pipeline, just through your array. So there are multiple ways of getting this correct. But if you do an enclosed object and want it transparent, often you'll get errors when it's trying to blend with itself. All right. So we've done the whole pipeline, the geometrical transformations, looked at those, rasterization, we added depth testing to that, GeoBlend. When we drew up the pipeline, we went through kind of something that could also be a test question, like what's the difference between per vertex lighting and fragment lighting? We kind of looked at what that would be. You could set that up similarly and just say, like, what's the difference between the effect? Number one, per pixel lighting means that the lighting is actually calculated each pixel. So a lighting effect like specularity will happen within the pixels of a polygon rather than just in the vertices. But it's more computationally heavy. So that's kind of the trade-off. Whereas vertex lighting means you calculate the lights only in the vertices, and then you basically do a gradient of the color over it, so you don't get specularity effects on a single polygon, just kind of on the edges between polygons. So it doesn't look as juicy, but it's a little bit lighter computationally. So that's kind of the effect or the trade-off that you start with. Then you say the difference. The difference is, rather than setting a varying variable, that's color, and then linearly interpolating that and setting it to the geofrag color, you set varying variables that are vectors, linearly interpolate those, and do the lighting in the fragment shader. Anything else that you imagine could be questions that you like to know how to answer? I can't put a kind of final list of all possible questions on the exam up here, but it's nice to know kind of, yeah, how detailed you need to be in your answers. Yes?
Bezier?
Yes. Okay, that's something that's kind of not within the scope of the pipeline itself, the Bezier curves. So basically, I think the examples that you've already done, you've seen some Bezier examples on some of the sample exams that I've shown you and done it in handouts, but that's something you need to kind of know how to do, at least similar in the way you've done it. If you have 4 control points of a Bezier curve, and I want to move along this Bezier curve starting at time x, ending at time, or starting at time t1, ending at time t2. Now, at the time t, where will I be? And that's the same thing. Start by calculating basically the value t. So you take the current time minus the start time, divided by the final time minus the start time. Then you have your t in the range from 0 to 1. And then you either have to memorize the formula for a 4 control point Bezier curve, or just understand how it works so you can kind of write it out. It's fairly simple to remember, especially if you look at the Bernstein polynomials that I think are explained in one of the exams. So yes, that's something you could get on an exam. Is there anything in particular I'd need to explain extra around that? I don't think so, because it's fairly clear the way I've been testing those until now. So yeah, Bezier curves. Is there anything else that we specifically looked at that is kind of outside the scope of this? Well, yeah, the Bezier curves and kind of intersections of rays and lines or rays and planes. You need to be able to do that. Like calculate t hit, p hit, figure out when something collides, or even be able to argue whether something collides or not by looking at the t hit value. Calculate t hit. If it's lower than 0, then it's something that would have happened in the past, so that's not something that I'm interested in. If I specifically say, does the collision happen within a certain frame time, then you have to make sure that it happens, that t hit is higher than 0, lower than the frame time. Then we can continue and calculate the p hit value. Intersections, reflections as well. Like if a collision happens and this is the normal to the plane that is collided with, what will the resulting reflected vector be? So questions like that as well. Anyway, other questions? Do you feel like I've covered everything for this exam? It's going to be super easy.
So it's basically going to be similar to the old, where there'll be some pseudocode you have to make and then just...
Yeah, I try to kind of mix it up, yeah. Calculations, some pseudocode may be one example of that, either shader code or, like in some cases, just graphics code. Like I want to take a function that draws a box like this, but make it draw a box that's like this. Things like that. So some pseudocode, probably mostly calculations, or like half of the exam, just calculations or going by hand through algorithms, things like that. And then a couple of examples that are just like these, written explanations. I try to mix it up in that way. And if you look through old exams, in some cases I'm doing a lighting calculation example where you do the calculations and end up with a color. In other cases, it's explain how lighting calculations work, what are the values used and how are they used, and you'd have to say, okay, I need the position of the light, the position of the vertex, and the position of the camera. I take a vector, that's the position of the light, minus the position of the vertex. I get the vector S, I get the vector V from the vertex to the camera, and then I do these dot products, or basically calculate angles between these vertices. So if it's a text example, you'd have to say that. I calculate the angle between them, which is the dot product divided by the lengths, or the cosine of the angle, sorry. And the cosine of the angle is a factor that's 1 when they're parallel, but 0 when they're 90 degrees to one another, which means the intensity will vary based on how directly the light is hitting the object. This gives me the values Lambert and Phong using these different vectors, and then I add those up, multiply them with the material values, the light values, and that gives me the final color. So yeah, I basically tried to take most of what we looked at and choose for each one. Do I set it forth as an algorithm or calculation example? Do I set it up as a pseudocode example, or do I set it up as an explanation test example? And you should be able to take more or less any of the subject matters that we've looked at and imagine that you could be able to answer them in any one of those three ways. That is, program around it, do the calculations as if as the hardware would do, or just explain what they are, where they happen, and why. Other questions? If not, I guess our time is up anyway, so have a nice weekend. See you Monday for like a harvest celebration of sorts, looking at some of the stuff that we've done over the semester. I hope I'll be able to prepare properly and have all of your programming assignments up and running. So other than that, see you then.